Hello everyone. In this lecture, we are going to talk about the notion of subsets. So we'll define the sets first. Subsets. Definition is given a set X, we say that it is a subset of Y if every element in the set X is there in Y, which means if you're choosing any element inside the set X, it should be there in Y also. For an example, I'm taking X as a set which has 1, 2, 3, and 4 in it, and the set Y as the one which has 1, 2, 3, 4, 5, 22, 0, and 99 in it. So every element of X, if you see, is there in Y. The element 1 is there in Y. The element 2 is there in Y. 3 and 4, both of them are in Y as well. So every element of X is in Y, and therefore X is going to be a subset of Y. The definition says every element of X should be in Y if we are saying that X is a subset of Y. So in this particular case, X is a subset of Y, but then Y is not a subset of X because if you see the element 25, 25 is not there in X. So if I want to assert that 25, if the set Y is a subset of X, I should show that every element in the set Y is there in X. But since 5, 22, 0, 99, none of these four are there in X, that means Y is not going to be a subset of X. Symbolically, we write it as, so this first statement is represented by these symbols. X is a subset of Y, so this is a symbol for subsets. X is a subset of Y. In the second case, Y is not a subset of X, so we write it like this. Y is not a subset of X. Now there is this general remark. If A is a subset of Y and at the same time B is a subset of A, then both of them are equal sets. For example, I've taken the sets X and Y here. If you see, every element in the set X is there in Y. So since every element of X is in Y, we have X is a subset of Y. Every element of X is in Y. So here we have X is a subset of Y. Similarly, every element of Y is there in X as well. Every element of Y is in X and therefore Y is a subset of X. And this tells me X is going to be equal to Y. So whenever two sets are such that one is a subset of the other, and conversely also, then X and Y, both of them are equal sets. The two sets are equal. Now, there's this one general remark here. The next result that we have is we're supposed to prove that phi is a subset of every set X. So to prove this result, I'll use the method of contradiction, just like we use method of contradictions to prove root 2, that root 2 is an irrational number. So I'll do the work along those lines. I'll start by assuming that by contradiction, to the contrary, let us suppose to the contrary, we assume that there is some set X. So we are assuming that there is some set X, let's say A, for which phi is not a subset of A. Now, if I'm saying that phi is not a subset of A, that would mean, per the definition of subsets, when we say that X is a subset of Y, we basically mean every element of X is in Y. Now, if you are saying that X is not a subset of Y, that would mean there is something in X which is not in Y. So since we have assumed phi is not a subset of A, it would mean there is something in phi, there exists an element in phi which is not there in A. But then this contradicts the very fact that phi has no element in it, which is a contradiction because phi is an empty set. Therefore, our assumption is wrong. And this tells us phi is going to be a subset of every set. So this proves our result. We wanted to establish that phi is a subset of every set. So we started by assuming, to the contrary, we assumed there is some set A for which phi is not a subset of this set A. Now, if we are saying something is not a subset of the other, that would mean there exists some element in the phi here which would not there be in the set A. But then this contradicts the very fact that phi has nothing in it. So, which is a contradiction as phi is an empty set. And therefore, whatever we assumed, which was that phi is not a subset of or equal to A, and therefore we'll have phi is a subset of every set X that is there. So for now, we just defined this notion of subsets. What we observed was whenever X is a subset of Y, every element of X is going to be there in Y. And then we have just established that phi is a subset of every set. Now we'll talk about how to find the subsets when the sets are given to us already. So here we have been given three sets. There is first set A which has only one element in it. There is a second set which has two elements in it. And there is a third set which has three elements in it. So we'll talk about how to find the subsets corresponding to each of these three sets. Let's let's do that. We have A is equal to the set which has one in it. We have the set B which has two elements in it. And then we have the three element set also. Now just a while back we said that phi is a subset of every set. So since we are looking for subsets now, I can just write phi for each of these three. Question says find all the possible subsets of A, B, and C. So phi, as we saw earlier, is a subset of every element, every set here. So let me do it like this. I'll first write all those subsets which has no element in them, zero element subsets. That's one. Here also we will have a one, this phi, and the phi here also. Then I'll write one element subsets. So I'll write all those subsets now which have one element in them. So if I'm forming subsets of A has only one element in it. So the subset I'm looking for would be this one, the subset which is the set which is having one in it. So in this particular case, all possible subsets would be, there are two in number. One is the phi itself and the other one is the A itself. So these are the only two subsets in the first case. In the second case here, I'll form the one element sets. That would be one here and that would be a two here. And then I'll form two element subsets also. So two element subsets would be these two contained in this set. So 1 comma 2 is the subset which has two elements in it. possible subsets become one is 5, the other one is 1 and then a 2 here, and the last one is this 1 comma 2. So these are the possible subsets and they are 4 in number. Here they are 2 in number, and then the last one, it's the 0 element set. I'll write the 1 element sets now. So this one, and then the one which has 2 in it, and then the one which has 3 in it. So I'm done with the 1 element subsets. Now I'll write the 2 element subsets, 1 comma 2, 1 comma 3, 2 comma 3. The 2 element subsets are done with, and then we are moving on to the 3 element subsets. That would be 1 comma 2 comma 3, and that is all that we are going to have for the number for the subsets here. And number of subsets would be, as we see here, 4 here, and there are 4 here. So they are 8 in number. So what you can observe is, when there is only one element in the set, we have 2 power 1 number of subsets. When you have 2 elements in the set, there are 2 power 2 number of subsets in the set. When there are 3 elements in the set, there are 2 power 3 number of subsets in the set. So there is this general result now. It says, given any set, if it has n number of elements in it, then its number of subsets would be 2 to the power n, which is what we had observed here also. We observed then that when we have a 1 element set, number of subsets are 2 power 1. When we have a 2 element set, number of subsets are 2 power 2. When we have a 3 element set, number of subsets would be 2 power 3. So here's a generalization here. Given any set X which has n number of elements in it, its number of subsets would be 2 to the power n. So we'll talk about the proof of this result, and I'll just borrow the result from binomial theorems. So let's see how to do this thing. I've been given a set X which contains n elements in it. I want to prove that number of subsets of X is 2 to the power n. So to do this result, I'll just follow the steps that I had used here. First, I wrote 0 element subsets, then 1 element subsets, then 2 element subsets, then 3 element subsets, and so on. So that's what I'm going to do here. I'll first write the 0 element subsets here, those subsets which are going to have 0 number of elements in them. So 0 element subsets would be, there is only one, and that is 5 for us. So there is only one set which has 0 elements in it. So, and then I'm going to use the notion of some ideas I'm going to borrow from permutations and combinations also. So I have n number of elements in the set, of which I'm choosing 0 at a time right now, which we can do in nc0 number of ways. So one element subsets would be, so those subsets which have only one element in them, I have n number of elements in the set, out of which I'm choosing one at a time. So that would be nc1 number of ways. Similarly, two element sets, that would be nc2. So that's how the counting goes for us, which means if I have to generalize, total number of subsets would be total number of subsets would be sum of the subsets, number of subsets which have no element in them, plus number of subsets which have one element in them, plus number of subsets which have two elements in them, and so on up to number of elements, number of subsets which have n number of elements in them. So, I have this expression with me, and I want to find the sum of this expression now. And here is where I'm going to use the notion of definition of binomial expansions. X plus y power n is given by nc0 x power n y power 0, nc1 x power n minus 1 y power 1, nc2 x power n minus 2 y power 2. One of the exponent is decreasing, the other one is increasing, ncn x power 0 y power n. But the expression that I have here has no x or y in them. So let me put n x is equal to 1, y is equal to 1 in this thing. When I put x is equal to 1, y is equal to 1, putting x and y equal to 1, I will have, on the left side I'll have 2 power n, on the right side I will have nc0 plus nc1 plus nc2 and so on up to ncn, which is also what I was looking for. I was looking for the sum of this expression, and the sum of this expression is equal to 2 power n, and this gives me the result I was looking for. This expression is equal to 2 power n, and therefore we conclude that total number of subsets total number of subsets of X which has n number of elements in them is 2 power n. So this proves the result we were looking for, which was given any set X which has n number of elements in it, number of subsets in it would be 2 to the power n. So we'll look at one problem based on this very result. Given any set X which has n elements, number of subsets of X is 2 power n. So here is a question based on this thing. It is, suppose that A and B are two finite sets with m and n elements in it, respectively. Total number of subsets of the set A, question says, is 56 more than the total number of subsets of B. And we are supposed to find the distance between P, which is having coordinates as n comma n. So we are looking for the distance between P and Q. So just a while back we saw this result. Number of subsets of a set which has a given number of elements is 2 to the power that number. So number of subsets of A, if I talk about, A has m elements in it. So number of subsets of A would be 2 to the power n, m. And then the other one has n number of elements in it. So number of subsets of B would be 2 to the power n. So this is the result we saw just a while back. Now question gives us there is a relation defined between these two numbers. Number of subsets of A is 56 more than the number of subsets of B. So number of subsets of A is 56 more than the number of subsets of B. This is the relation I have. 2 to the power n is equal to 56 plus 2 to the power n, and then I want to solve this equation for the values of m and n. So what I'll do is I'll shift this 2 power n on the left. 2 power m minus 2 power n would be 56. M is supposed to be a larger quantity because of this relation. So I'll have 2 power n times 2 power m minus n minus 1 is equal to 56, which can be factored as 2 cube into 7. And then I can do a comparison here. N would be equal to 3 and 2 power m minus n would be equal to 7. Now since I already have the value of n as 3, m will come out to be 6 here. Shift the 1 on the right side, it becomes 8 on the right side. So it becomes 2 power m minus n is equal to 8, and that gives me m minus n is equal to 3, and that gives me m is equal to 3 plus 3, which is the value of n. N is going to be equal to m is going to be equal to 6. So we have found the value of n, we have found the value of n. Coordinates of P, which were m, n, would be equal to 6, 3. And we are looking for the distance between this point P and the point Q, which is -2, -3. So the distance would be PQ, a 6 plus 2 square, a 3 plus 3 square, and a 64 plus 36, that would be 100. Root of 100 is 10. So the answer we are having is 10. The PQ is going to be equal to 10. So this is one problem based on the application of this result. Total number of subsets of a set which has n elements in it is given by 2 power n. So in this particular case, we observed there is a relation 2 power m is equal to 56 plus 2 power n. And then I tried to solve for m and n, which gave me the value of m as 6, n as 3. And then since we were talking about the distance between the two, I just used the distance formula to find the distance PQ. PQ is going to be equal to 10. Let's see a few more problems based on subsets, the notion of subsets itself now. So here is one question we have. It says, suppose you are having a set A which has 1, 2, 3, 4, 5, 6, 7 in it, and there is another set B which has the 3, 6, 7, and 9 in it. We are supposed to find the number of subsets in the set, or we are supposed to find the number of elements in the set. Now, what does this set look like? This set looks like, question says, it has collection of all those subsets of A which have nothing in common with B. C intersection B should be non-empty. So it is supposed to be non-empty. So let's talk about this question then. I have been given a set A. A has 7 elements in it. I have been given the set B, which has 4 elements in it. And then I'm supposed to find number of elements in the set which have something in common with B. So one thing is I'm choosing subsets of A. The second thing is I'm choosing those subsets of A which have something in common with B. So let me find all the subsets of A. What I'll try to do here is I'll find all the subsets of A from which I will subtract those which have nothing in common with B. That will give me the number of subsets which have something in common with B. This is how I'm going to do it. Let's find the total number of subsets of A first. Total number of subsets of A would be 2 to the power 7. Total number of subsets of A would be 2 to the power 7. That would be equal to 128 here. And then I want to find all those subsets which have nothing in common with B. So total number of subsets we have found. Total number of subsets of A is 2 to the power 7, which is 128. Now coming to the total number of subsets, I'll find the subsets, those subsets C of A, which have nothing in common with B. So what I'm trying to find in this case is number of subsets of A which have nothing in common with B. The result I'm looking for is supposed to be all those subsets which have something in common with B. So I have started by saying, let me find those first which have nothing in common with B. So those subsets C of A which have nothing in common with B. Now, if I'm choosing that subset of A which have nothing in common with B, that means while forming the set, I cannot take any of the elements which are here because I don't want anything in common with B. So the element 3 I cannot and should not take. So is the case with 6 and 7. So I can, while forming the set C that I want, can choose any element from the A except these three elements. Because if I choose these one of these three, this thing gets violated. I want nothing in common with B. So C should be formed, she should be a C should be a subset of A formed out of the elements 1, 2, 4, and 5, which means total number of such subsets would be, there are 4 in number, these elements. So total number of subsets would be 2 to the power 4, which is 16. So there are 16 subsets of the type C which have nothing in common with B. But since this is not what I'm looking for, the question asks me to find all those subsets of A which have something in common with B. This is the case where I have nothing in common with B. So the total number of subsets, total number of subsets of C which have something in common with B, the total number of subsets of A which satisfy C intersection B not equal to 5, they would be from the total number of subsets of A that I have, which are 128 in number. I'll subtract the number 16 to get the answer 112. So this is the answer I'm gonna have. Question was, what is the number of elements in the set? I observe there are 112 elements in this set. So to summarize again, I have been given two sets A and B. Question is asking me what is the number of elements in the set. The set is collection of all those subsets of A which have something in common with B. C intersection B is not equal to 5 means something is common with B. So that's what I did. I found the number of subsets of A first. A has 128 elements in it. Then, instead of finding those number of subsets which have something in common with B, I started by finding those number of subsets which have nothing in common with B. I observed there were 2 power 4 which is equal to 16 number of elements in the set. 16 such subsets are there which will have nothing in common with B. But since I required those subsets which have something in common with B, from the total I subtracted the case where there is nothing in common with B, and that gives me the answer 112. So this one question based on subsets. Then again, question is, suppose we are given a set S which has 100 elements in it. I'm supposed to find number of non-empty subsets of S, non-empty subsets A of S, such that product of elements in A is even. So I want the product of elements in A to be even. Then again, I'll try to do something similar which I did here. One thing is I am being asked to find the number of non-empty subsets of S such that product of elements in them is even. I want the product to be even. So let's do this thing. First, let me find all possible subsets of A that are there, subsets of S. Total number of subsets of S are total number of subsets of S would be 2 to the power 100 because the set S has 100 elements in it. Now, what I am looking for are those subsets of S in which product of elements is even. So instead of finding the sets which have product even, let me find the sets which have product odd first. So those subsets, number of subsets of S in which the product is odd. Number of subsets of S in which the product is odd. Now, if you want the product to be odd, the subset you are taking should be taken out of, let's say, it will be 1, 3, 5, so on up to 99. I cannot choose a single even number because as soon as I choose in the subset that I'm forming, if I choose a single even number, the whole product becomes an even. So I cannot allow choosing of this subset, choosing of an even number in the subset I'm forming, which means I need to choose elements from amongst these numbers that are written here. There are 50 such numbers here. So total number of subsets in which the product is odd would be 2 to the power 50 minus 1. I'm doing this minus 1 because if you remember, when we write number of subsets of any set, phi is always there. But since I want the product to be odd in this case, I'm discarding this phi from the possibilities I have. So 2 power 50 minus 1, this 1 is to exclude the case where the empty set is also there. So we subtracted 1 because we want to exclude that case where number of subsets could have been, the phi could have been included. Subtraction of 1 is to exclude the inclusion of phi. Now, required number of subsets I was looking for. Now, total number of subsets are 2 power 100. Amongst these, there are those in which product is odd, 2 power 50 minus 1. But even in this difference that you have taken, there is one subset and the phi is the one. So I need to exclude that phi. Then again, I excluded that phi here. As soon as I excluded the phi here, it came here. But then I don't want that phi here either because I want the product to be even. So I'm excluding that phi from discounting as well. And that gives me 2 power 100 minus 2 power 50, which is going to be same as 2 power 50 into minus 1. So that's the answer we have, 2 power 50 into 2 power 50 minus 1. So what happened here is we had a set given to us which had 100 elements in it. We wanted to find number of subsets, non-empty ones, of A of S such that product of elements in them is an even number. Now to get the product even, I started by considering the product odd case. If I want the product to be odd, I need to choose the subset in such a way that the elements of it are coming out of 1, 3, 5 and so on up to 99. There are 2 power 50 subsets of this set in which one of the subset is phi. I excluded that phi because I wanted the product to be odd, but phi has nothing in it, so I can't assert anything about product being odd there. Now required number of subsets would be total minus this number of subsets. But then again, as soon as I had excluded the phi here, it came here. So I excluded the phi here as well. And that gave me the result 2 power 50 into 2 power 50 minus 1, which is the option A for us. Next, we have the notion of Venn diagrams. So I'll just illustrate it briefly. So we have seen some operations related to sets already. We have talked about the union operation when two sets are given, which can be extended to finite number of sets also. For example, we can talk about A union B union C and so on. So we have talked about three operations so far. One was union of sets, second one was intersection of sets, third one was difference of sets. So when we want to express those operations diagrammatically, we use the Venn diagrams. Now, here is how we do it. The universal set is denoted by this rectangle. Now, the sets that you have A and B are denoted by the circles inside the rectangle. Let me mark the A here. Let's suppose this is the set A, this is the set B, and then we'll talk about the three operations that we have discussed earlier. So in the first one, I'll talk about the union operation. In the second one, I'll talk about the intersection. In the third one, the difference. In the fourth one, another difference. That would be B minus A here. So let's talk about the operations that we have then. If you remember when we were talking about union of two sets, we were saying we'll collect elements of both of these sets, of the set A as well as the set B also. So to denote the fact that I'm including both the elements from both the sets, we mark the region of both of them. So the region for A, I'll mark it to denote the fact that I'm including the elements from the set A, and then I'll mark the region of B also to denote the fact that I'm including the elements of B as well. That's one thing we have. For the second one, I have intersection. In the intersection, we include the common portion, and the common portion that I see between A and B is this one. This is there in A, and this portion is there in B as well. So the intersection would be this common portion here. So that's the common portion we have denoting the intersection of the two sets. And then the other two that we have are A minus B and B minus A. A minus B definition was you are supposed to include elements of A alone, not the B. So we are choosing elements which are there in A but not in B, and they are here, this portion. I can't include this portion this time because it is common to both of them, and I want the portion of A alone. So Venn diagram for A would have this thing, the region of A alone. Same thing happens with B minus A this time. So B minus A would have the region of B alone, not the A, and that's it. So this is the Venn diagram for the four operations that we had. A union B has elements from both of them. A intersection B has elements from this portion, common one. A minus B has the portion of A alone, not the B. B minus A has the portion of B alone, not the A. So we'll see one result based on the which relates the union operation with the other operations, should I say. So let's see what I'm talking about. I want to establish this relation union of A and B. Number of elements in the union of A and B is actually equal to number of elements in the set A plus number of elements in the set B minus number of elements in the set A intersection B. I'll refer the Venn diagrams then again. So let me consider the set. So I have the A with me. I want the B with me. I have the two sets with me, A and B. This union that we have, which we are familiar, is this portion. The union of A and B is this portion. It can be considered as the region comprising of three different regions, the disjoint regions. One is the region here, which is the region of A alone. That's one region we have. Second region I can take is this one, the region which is common to them both. And the third region that we can take is this one. So this one. So I have these three distinct regions. These three are disjoint. So the A union B, I can regard it as the A union B can be written as the region comprising of A minus B, which is the region in blue, plus the union, the intersection of A and B. And the third region is this yellowish region, which is denoting B minus A. So this is what I'm observing. The A union B is a union of A minus B, A intersection B, and B minus A, all three of which are disjoint sets. Now I wanted to find number of elements in A union B. So number of elements in A union B would be equal to number of elements in A minus B plus number of elements in the intersection plus number of elements in the B minus A. So what I'm basically saying is the union in the whole of it is actually equal to union in the blue region, then number of elements in the blue region, number of elements in the middle portion, and the number of elements in this portion. Summing up all these three elements from here will give me the final thing. So number of elements in A minus B now. A minus B is this portion, which I can obtain by subtracting from the A the intersection of A and B. That's one thing. Second thing is intersection, which is fine. The third thing that I have is n of B minus A, so which can be written as then again number of elements of B minus number of elements in A intersection B. If you want to get the number of elements in B minus A, which is this one, just subtract from the whole this portion. That's what I'm writing here. From the whole of B, I'm subtracting this portion to get the B minus A. Now it's just simplification, which gives me number of elements in A union B is equal to number of elements in A plus number of elements in B minus the number of elements in A intersection B, which is also the result we were looking for. So I started by saying union of A and B is composed of three regions, three disjoint regions, A minus B, A intersection B, and B minus A. So to get the number of elements in the union, I can simply sum up the elements, number of elements in the three disjoint sets here. number of elements in A minus B plus number of elements in A intersection B plus number of elements in B minus A. But then number of elements in A minus B can also be written as number of elements in A minus number of elements in A intersection B, and so on. And then you simplify at the end to get this result. Number of elements in A union B is equal to number of elements in A plus number of elements in B minus the number of elements in A intersection B. So this result is done. So there is this one more result which says, just like for union of two sets, you have this relation number of elements in the union is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Similarly, there is a relation which we have for union of three sets as well. Number of elements in the A plus number of elements in B plus number of elements in C minus number of elements in A intersection B, A intersection C, B intersection C, lastly, plus number of elements in A intersection B intersection C. Now this result, I'll prove it using the distributive property we have talked about when we were talking about the operation on sets. So let me start it. I'll start by taking this B union C as a single entity. Let me call it as a X. So I want the union of A union B union C. I already know the operation of union is associative and commutative as well. So this set N A union B union C, number of elements in the union would be equal to number of elements in A union X. As soon as I write A union X, I come back here. I can use this last result I wrote. That would be number of elements in A plus number of elements in X minus number of elements in the intersection. And then number of elements in X, if you talk about, is simply the number of elements in the union of B and C. So it's gonna be same as number of elements in B plus number of elements in C minus the number of elements in the intersection of them both. That's what I'm gonna write here then. Number of elements in X is equal to number of elements in B plus number of elements in C minus the number of elements in the intersection. And lastly, we are supposed to deal with this A intersection X also now. So let's see what to do with this A intersection X now. Let me deal with it separately. Number of elements in A intersection X is what I'm looking for. But then X, as we had mentioned earlier, was B union C. So what we have is A intersection B union C. And here is where distributive property comes in play. Distributive property, if you remember, was A intersection B union C is given by A intersection B union A intersection C. And then again we have a union here. So it would be same as number of elements in A intersection B union A intersection C. And then again we come back here. Union of two sets is given by this relation. So we have a union of two sets. This is the first one. This is the second set. So union of two sets is what we have. So I'm looking at union of X and Y basically. Union would be number of elements in A intersection B plus number of elements in A intersection C minus number of elements in A intersection B intersection A intersection C. A intersection A is anyway going to be equal to A itself. So let me just take one of them only. It's same as A intersection B intersection C. Now I can use the two results that I have. Equation 1 gave me one relation. Equation 2 gave me the other. Now when I combine these two results, I get the desired relation that I wanted. The relation is number of elements in A union B union C is equal to number of elements in A plus number of elements in B plus number of elements in C minus the number of elements in A intersection B, B intersection C, A intersection C, and lastly the intersection of them all. So at last I would just take up one question based on this result. Union of A and B has number of elements in A union B is equal to number of elements in A plus number of elements in B minus the number of elements in A intersection B. So here is what we have then. The question gives us there are 200 individuals with a skin disorder. There are 120 people who were exposed to the chemical C1. There are 50 people who were exposed to the chemical C2. 30 were exposed to both of these chemicals. So question says 120 were exposed to the chemical C1, which means they are saying, let me, if I'm using the symbol C1 and C2, C1 to denote the number of, to denote the people, to denote the set of all those people which were exposed to chemical C1. I'm using C1 to denote the set of people who were exposed to chemical C1, and that the question says has 120 elements in it. The second set is I'm using C2 for this one. Number of elements in C2 is given, and that's 50 given to you. There are 30 individuals who are exposed to both the chemicals. Both the chemicals means the common portion they are talking about, which is the intersection. So they have given you the intersection also. Number of elements in C1 intersection C2 is 30. So this is the detail that is given to me. And now we come to the question they are asking. Find the number of individuals who were exposed to chemical C1 but not C2. Second one, chemical C2 but not C1. Third one, any of the two. So we'll talk about the first one. The Venn diagram would be a C1 here, C2 here. Question says in the first one, find the number of people who were exposed to the chemical C1 but not the chemical C2, which means they are talking about C1 alone. So the region I'm looking at is the region for C1 alone, and C1 alone is this portion here. So this is the region I want to find. Number of people who are exposed to the chemical C1. C1 alone is the case. So number of people who are exposed to C1 only would be from the whole of C1, let me subtract the middle portion, common one. From the whole of the portion, if I subtract this one, I will get this shaded one. So that's what I'm doing. Number of people who are exposed to chemical C1 only would be 120 minus 30, and that gives me 90. Same thing I'll do for the C2 also. I have been given two sets C1 and C2. I want to find number of those people who are exposed to chemical C2 alone this time. Find the number of people who are exposed to chemical C2 but not C1. So the shaded region in this case would be this other portion this time, the region of C2 alone. Number of people who are exposed to chemical C2 would be this one. And just like the last one, to get the number of people who are exposed to C2 only would be number of people from the whole of the set minus the number of people in the common region, which is 50 minus 30 for me. The answer is 20 here. And lastly, I want any of the two. Question says, find the number of individuals who are exposed to chemical C1 or chemical C2. Now, when they are saying this or, they are saying we are just counting those people who are in any of the two sets. So whether it is in C1 or it is in C2 doesn't matter. We are counting a number of elements from both of them. So basically they are talking about the union of the two. So when they use the word or, it's the union they are referring to. When they use the word and, they are referring to the intersection. So union is what I want to find here. So number of elements, not the A, it's not the B, it's C1, C2 here. So number of people who are exposed to either C1 or C2 would be the formula simple. C1 union C2 is what we are looking at. That would be number of people who are exposed to C1 plus number of people who are exposed to C2 minus number of people who are exposed to the both. Number of people who are exposed to C1 was 120. The number of people who were exposed to C2 was 50, and then the 30 for the third one. And that gives me the answer 170 minus 30, which is gonna be 140. So it's mostly about you trying to figure out what region things represent. You can choose to use this formula to solve the problem, or you can just answer based on the Venn diagram itself. We'll talk about more such problems in the next class, word problems on Venn diagrams. So that's it for the day. That's it for the day. Thank you everyone and have a good time everyone.